Welcome to today's video. In the previous video, you remember we saw curves and vectors on a manifold, and in particular vectors as elements of the tangent vector space at a point in the manifold. We saw how we can define coordinate bases of vectors that are the partial derivatives, the vectors tangent to the coordinate curves that actually map to the axis in Rn through the mapping that translates the manifold to Rn. And today we're going to see the notion of Oneforms. Now, what are Oneforms? Well, a Oneform, I call it omega with a serifa, is a real linear functional over the tangent space. So what does that mean? Well, it's a map that takes elements of the tangent space, takes vectors, its vectors, and spits out real numbers. That's what it does. And I notate it like that. Omega acts on the vector v. V is an element of TPM, of the tangent vector space to the manifold M at the point P, and acts producing this bracket that I have here, this notation, and this is of course a real number, as it should be. This is an element of TPM, this is an element of the reals. We can define, similar to what we did in the video about algebra, we can define the given a basis. Remember, this epsilon A is a set of a basis. It's an arbitrary basis of vectors in the tangent vector space to the manifold at a point P. There is a unique set of Oneforms that I call epsilon super A, okay? So the vectors, the set of vectors, the index in the set of vectors is an index downstairs. This is not a component, every element. So just a reminder, this is the same as writing epsilon 1, comma, epsilon 2, comma, epsilon n, right? Each of them is a vector. And same here, we get epsilon 1, comma, to epsilon n, each of them a Oneform, okay? So we have a unique set of Oneforms with the index that notates as elements of the set upstairs, a super index, such that the action of every element of an element, the eighth element of the set of those Oneforms acting on the B element of the basis of TPM that we're considering gives me the identity, the Kronecker delta. Now we call the set epsilon super A the dual basis, of course to the basis epsilon sub A, of the vector space T star Pm. T star Pm is the name of the vector space of Oneforms at the point P in the manifold. We call that the dual space to TPM and also the cotangent vector space. Remember, we call this one the tangent vector space to the manifold at the point P. This one will be the cotangent vector space to the manifold at the point P. Now, this means that I can now compute the action. Knowing this, I can compute the action of an arbitrary Oneform on an arbitrary vector. So if I have an arbitrary vector V, that is, of course, I can write in terms of its components summed times the elements of the basis summed. Notice that I use A and not mu or anything like that. Remember, I use Latin in this, the convention I'm going to be using in differential geometry is Latin ABC is for arbitrary basis, then mu, nu, sigma, etc. is going to be for coordinate basis here, okay? All right, now this is an arbitrary vector, an arbitrary element of TPM, okay? And I'm going to write, of course, any vector I can express as a linear combination of elements of the basis, and I can write an arbitrary Oneform omega, same way, the components omega sub A, epsilon super A. So I have here an arbitrary vector, an arbitrary Oneform. So now we can write the action of the arbitrary Oneform omega on the vector V as omega acting on V. Well, that will be equal, let's just express omega in the basis, omega A, epsilon A, comma, V A, or VV, let's call it V, B here, epsilon B. All right, now of course this is bilinear, so I can take out omega A V B, and then I'm left with epsilon A epsilon B. Right, and this is the dual basis to this one, so we know that this is the delta AB, and therefore this thing is omega A, omega B, delta AB. And the delta, the identity, transforms the B into an A, so this is omega A, VA. We call this the contraction as well of omega and v. Notice that if omega is a linear functional on v, so on the one forms are linear functionals on the tangent space, then the vectors are linear functionals on the cotangent space. You can read it as who's multiplying who, right? So that means that the dual of the dual vectors, tangent vectors to the tangent vector space to the manifold M at the point P is exactly the tangent vector space to the manifold at the point P. Notice, by the way, that this may remind you of the inner product that you've seen in your quantum mechanics. I mean, and for good reason, it's kind of related in a way. But notice that this cannot be an inner product, not at all, because vectors and one forms, they live in different spaces. They're apples and monkeys. You cannot take inner product between apples and monkeys. So don't call this an inner product because it's not like an inner product. It's not an inner product at all. Okay? Again, objects from different spaces. It will take a long while until we have the structure to talk about something like an inner product. And it's definitely not yet. Do you think that you know what you need in order to be able to take inner products? We first need to have a metric, and it will be a long time until we have a metric. We will have curvature before we have a metric. Anyway, so the notion of one forms has been introduced. I hope it's clear. Let's now get to a very interesting one form that you may recognize from previous calculus courses. All right, notice that each function f defined over the manifold actually can be used to define a one form, a specific one that I'm going to call df at the point P, that we are going to call the differential of the function f. And I define that one form as follows. I say that the action, one way of defining a one form is telling me, okay, what is it? Because it's a one form is a map from a linear map from vectors to the reals, right? I can tell you how the one form acts on all the vectors. And it acts by, okay, if I act with df on the vector, it returns the directional derivative of the function in the direction of the vector. That is the vector acting on the function. Now, what is this? So, do you remember from your vector calculus something like a vector that when you do something like a scalar multiplication by a vector, you get the directional derivative? What was that vector? Let me tell you what it may remind you of. You had a vector v, and then you wrote like, oh, you're a dot product. I mean, I know this is not an inner product, but you wrote something like that, right? And that gives me the directional derivative with respect to the vector v, usually notated like that, of the function f, right? You remember that? That this is the directional derivative? So, literally, this is kind of analogous to that. Let me erase this. When I act with this form on the vector, it returns the directional derivative of the function in the direction of the vector. This thing is generalizing the gradient. So, fun fact, the differential of the function is like the gradient. It is the gradient, the differential of the function. Maybe there's a relationship between the two. Maybe this is a generalization of the gradient that you saw from calculus. Maybe you need to be more convinced about that because you know, but hold on, the differential of the function I learned from my vector calculus, right, is something more like partial f partial x dx plus partial f partial y dy and so on. No, that's the differential. Okay. But if this were a vector, if the differentials were vectors, then this would be a vector, this would be a vector, maybe vector of a basis, and those would be the components. And these components, if you put this in a component, right, isn't that really the gradient of f? So maybe the differential and the gradient are actually the same thing. Maybe the gradient is not really a vector, rather a covector. I don't know. We'll see. You may need more convincing, but I hope you start saying, I did a stretch, right? I told you that these can be elements of a basis of some kind. Well, I don't know. Let's see. So if we are given a one form omega, and I'm asked, okay, please find me the components of the one for omega. I know there's the omega sub a, right? But okay, no, I mean, just give me an operation that returns the components. What would be that operation? Well, I can contract omega with the elements of the basis of vectors, right? That is dual to that one. So if we do that, we get that this thing is omega a, epsilon super a, epsilon sub b, right? I take the factor out, omega a, and this thing now becomes, well, I'll write it, epsilon A, epsilon B, which is the same as delta AB, the identity, and that means that this is omega B, right? All right, so you see, if I get omega and I contract it with the element of the basis of the tangent vector space, epsilon B, that returns the component omega B of the one form. We can do the same in order to find the components of the differential of the function. Well, it's a one form, it's a covector in a way. What are the components? Well, let's use the same logic. So the components are going to be I act with a df on epsilon sub mu. This is, I'm acting on a coordinate basis to get the components in a coordinate basis. So I want the
components of df in a coordinate basis. So the coordinate basis would be epsilon sub mu. Right.
Okay, cool. So I know that this is going to be the action of epsilon sub mu on F. But what is that action? Remember, the epsilon mu's act like partial derivatives. They are representing the tangent vectors to the coordinate curves. They're the partial derivatives with respect to the axis. So this thing is the partial mu of F bar. If you remember, the F bar is the F that takes the coordinates of a point in the manifold and returns the function of the point of the manifold. So certainly, this thing, the components of the differential of F are the partial derivatives of the function as a function of Rn. So certainly those are the components that the gradient has. This is the freaking gradient. The components of the differential of F are the components of the gradient of F. We have generalized the notion of gradient. We have generalized the notion of gradient to a manifold. In the differential of a function is the gradient of the function. All right, so okay, you may be okay, but again, and you will tell me, but again, I remember that the F was partial F, partial x1, let me write it like that, dx1 plus partial F, dx2, and so on, right? Is it really that? Is it really that? Can I understand it as that? Well, let's see. Why don't we take the differential of the coordinate curves and see what they are? Shall we? Before doing anything, a little reminder. Remember from the previous video that f of a point in the manifold is the same as the f bar of the coordinates of the point in the manifold. All right? So imagine now that I define as a function the function that takes a point in the manifold and returns the muth component of that point in the manifold in a coordinate basis. Okay? So if I do that, the function df is the same, if you want, as the function of the, let me write it like that, let me call that function x mu. Okay? What is the differential of x mu? So the function, this is like the equivalent in calculus as saying f of x vector is going to return the x component. And then g of the x vector is going to return the y component. Okay, so this is the kind of function we're talking about here. Takes a point and returns the muth coordinate. All right, so what is the differential of the x mu, the muth coordinate, right? What is the differential of the coordinate function? Well, let's see. So I compute, what is the, so this is gonna be dx mu. This is a differential, right, of a function, and therefore it's a one form. And I want the components of the one form, so I can act on the elements of, let me call nu, of a coordinate basis, epsilon nu, and see what I get. All right, so if I do that, I know from that definition that this is going to be the epsilon nu, acting on the coordinate x mu. That's what it's going to be. On the function, this is understood as the function that returns from a point x in the manifold, the coordinate x mu. But what is that? This is literally partial nu x mu. Oh, get this crap out of the way. So, what is the result of that? Well, you know what that is. This is the delta nu mu, right? If partial with respect to x of x is 1, partial with respect to x of y is 0. Unless this nu is the same as the mu, this is 0, and is 1 otherwise. Oh my god. So, the dx mu is the dual basis. This is literally the definition of the dual basis. Remember, the definition of the dual basis is, with an a here and a b here, is the basis that satisfies when the set of one forms that acting on a basis of vectors returns the delta, the identity. And that's exactly what this is doing. So I found the dual basis. Remember, if the basis of vectors can be identified with the partial derivatives, remember that the epsilon nu, the elements of a coordinate basis, act on functions from the manifold to the reals the same way that the partial derivatives act on the f bar from the real act on the f bar that takes points from Rn, the coordinates of x in the manifold, to R. So if these are the partial derivatives, then the dual basis to the partial derivatives to the tangent vectors to the coordinate curves are going to be the dx mu. So we can identify elements of the basis, of a coordinate basis with the partial derivatives, and elements of the dual basis with the differentials. Aha! So that means that I can think that in a coordinate basis, I can write a one form omega as some coefficient omega sub mu, contracted of course with elements of the basis epsilon mu. But I can, abusing a little bit but equivalently, omega sub mu dx mu. So the differentials of the coordinates are certainly basis, in fact the dual basis to the partial derivatives in the cotangent space, a basis of the space of one forms. So that means that certainly the differential of a function is going to be equal to the components, let me write it like that, the components in a coordinate basis, the components of the differential of a function contracted with the epsilon mu. And these are going to be the components, we already computed what they were, the components are the partial derivative with respect to mu of f bar, and then these ones are the dx mu. So indeed, this thing is literally this one. You see? I mean, oftentimes in text, you would find this without the bar. I mean, we just keep it because we are nice like that. But again, this is the partial derivative of the function f bar, which is the one that takes the coordinates, remember, of the point in the manifold from Rn to the reals. So this is literally this. Now you know truly the differential of a function is its gradient, and the components of the gradient are literally the components of the gradient that you know and love from your calculus. So now you learn that the gradient is not a vector, it's a covector, it's a one form, the gradient of a function. And it's also the differential of the function. So these different notions that you had of the differential of a function, the gradient. Well, they're kind of the same. The gradient of the function is the differential of the function. It's you just if you collect the components in a coordinate basis, you get the usual gradient the way you defined it. Now you might be wondering at this point, but the gradient only had that form in Cartesian coordinates. It had a different form in spherical coordinates, right? And things like that. Yes, and we're gonna get to that because in life there are two kinds of bases, coordinate bases and non-coordinate bases. And the true understanding of coordinate bases and what it means to do changes of bases will actually be acquired in this introduction, hopefully. Wonderful, so we understood the one forms, we understood the differential of a function, which is a one form that happens to be the gradient of the function as well. And now you may wonder how you change from basis to basis. Well, the change of basis is going to be given, remember, if the components of the vectors transform with lambda tilde, the components of the one form will transform with lambda. Let's just write it. Remember that lambda mu nu is the Jacobian, is partial x nu, partial x prime mu. All right? Wonderful. All right, so the changes of coordinate bases from one coordinate basis to another of these objects is very similar to what we saw when we saw the introduction in video 2 about the linear algebra equivalent to this. So, vectors of the basis of the tangent vector space, they transform with lambda. The vectors of the basis of one forms, or the basis of T star Pm, or the covectors if you want, transform with lambda tilde, and respects the index structure that we already know from the algebra video. Same goes with the components, but opposite. V prime mu, the components of a vector in the tangent vector space in a point transform with lambda tilde, and the components of a one form transform with lambda. Those are changes of coordinate bases. Before we continue, a quick question. But you just told me, but how do you know that the components of one form transform with lambda? Okay, so just quickly so you see, that is equivalent to showing based on the video that with the second video that we recorded. It's proven out of demanding that the elements of the dual basis transform with lambda tilde. Now that makes sense, right? I mean, the differentials transform with the Jacobian matrix like that. So of course it has lambda tilde. How do I know that the coefficients transform with lambda? Well, you do the same thing as we did in the second video. So here we demand that the dual basis, so we know how the vectors of the basis transform. They transform with lambda, the vectors of the basis, and we demand that when we transform to the new basis, to the prime basis, it's still, I know how this transform, I know what this is. This is supposed to be a nu. This thing is lambda nu mu epsilon mu, right? That's what this is, that I know, okay? And then I know that this thing would be whatever the matrix is, let's call it an unknown, and the whole contracted thing has to be equal to the identity. It's very similar to what we did in video 2. I actually recommend that you repeat it in this case and prove to me that the elements of the basis of one form transform with lambda tilde, and therefore that means that the components of a one form transform with lambda. All right. Now I think the moment has arrived for me to just talk with you like 5 minutes about the difference between a coordinate basis and a non-coordinate basis. All right, let's have a discussion about it. All right, so remember that a basis could be a coordinate basis or not. In fact, I said, I write for an arbitrary basis, I write Roman indices, and when I write Greek indices, it's because I know it's a coordinate basis, right? Right, what does it mean to be a coordinate basis? Let's remember, that means that the vectors of the basis are tangent to, so you see, the vectors are, if this is x1, x2, x3, right? This vector is partial 1, this vector is partial 2, this vector is partial 3, in the sense that those vectors are the tangent vectors to the coordinate curves. When I go from -1, this is the vector epsilon 1, this is 1, no, epsilon 3, this is the vector epsilon 1, the tangent to this curve, right? And this is the vector epsilon 2, right? The tangent to those curves. Well, I'm not going to prove this theorem here because it requires a little bit more to prove, above all, the sufficiency part, okay? But a basis is a coordinate basis if and only if the elements of the basis commute, all of them. The necessary part is kind of easy to see because partial derivatives with respect to coordinate axes, right, in Rn, they do commute. Let's see, for example, examples of a basis. Imagine that I give you, for R, a manifold of dimension 2, and I give you that, let's say for R2, for example, I give you this element of the basis is going to be partial x, and this element of the basis is going to be, partial y. Well, that's certainly a coordinate basis, right? In fact, this is going to be, this is R2, there's going to be, this element is this element is this one. All right, cool. How about if I do plus partial y and minus partial x? Well, this is also a coordinate basis, right? I mean, we can compute the commutator. What's the commutator of partial x plus partial y with partial y minus partial x? And this is 0 because partial x commute with partial x commute with partial y, right? So this thing is also a coordinate basis, and in fact, it would be a rotated basis. This is the 45 degree here, and then I have partial y minus partial x, something like that. All right, so it is a rotated basis with respect to that one. Now let's do another example. How about this one? Okay, how about this guy? Well, this one's certainly a basis in the sense that you can span any direction combining these two. But I introduced some dependence on the point. Let's see, is this a coordinate basis? Well, let's compute the commutator of epsilon 1 with epsilon 2. If we do that, we get that epsilon 1 would be y partial x plus partial y. Then this thing acts on partial y. And let's act on a function to make it easier, because that's the easiest way to compute these things. Then acting on a function, then minus partial y, and then I get y partial x plus partial y, acting on a function. All right, so what do I get? I get y partial x partial y f plus partial second of f with respect to y minus, and I get partial y acting on y partial x f minus partial second y f. This cancels that, all right? And I'm left with this expression. Now, if I continue this way, let's continue here. This expression, the first one gives me y partial x partial yf, and the second one gives me, using Leibniz rule, you get partial x f plus y partial x f, right? And then this one cancels this one, but the total result is minus partial xf. So if you remove the f's, we found that in this case the commutator of epsilon1 with epsilon2 is minus partial x, which is different from 0. Therefore this is not a coordinate basis, even though it is a basis. It changes with the point, right? The two elements of the basis change as I move through the manifold, but that's okay. You can still, but that's what happens with your spherical coordinates, right? The direction of the vectors of the basis is changing depending on the point you are. That's okay, that's a basis. It so happens to be not a coordinate basis here. We will discuss more about spherical coordinates, don't worry. But you see, this is an example of non-coordinate basis. I hope that's understood, and now that we've understood the notion of vectors and one-forms well, and changes of basis, we're going to define tensors in a manifold. All right, the notion of tensors. So what are tensors? Tensors are multilinear maps that act on this space that I call TTRS. So at a point in the manifold, I got R copies of the cotangent vector space and S copies of the tangent vector space, and then the tensor, a tensor type RS, takes these R copies and these S copies of the cotangent and the tangent vector space and returns a real number, and maps it to real numbers. Okay? Now, notice that I say type, not rank. I am really against calling the type of a tensor rank, even though you will hear it around, for reasons that I have and I can explain to you. But let's call it type in this course, okay? So tensor of type R0 are the contravariant tensors, so the components will have R contravariant indices, and 0s are the covariant tensors. The components will have S covariant indices. Now, what are those components that we're talking about? Well, the components of a tensor is what you obtain when you act on elements of the basis of the tangent and cotangent vector spaces, right? So if I take the tensor T, that it's R one-forms and it's S vectors. So if I act on R copies of vectors of the basis, right, and S copies of vectors of the basis, that will give me the component T A1, A2, AR, B1, B2, yes. Don't get intimidated by this notation. We can do it with 2, mu, nu. What is that? Well, that thing is take the tensor, right, and act on upsilon mu and upsilon sub nu, all right? So that is the component of the tensor. That is actually neat because that means that what would be the action, so if I want to compute the action of the tensor on, say, a one-form omega and a vector v, what would that be? Well, I get the component T mu nu that I had here, and then I contracted with omega mu v nu. And that comes from just substituting in the action, because this is a linear map, right? And you substitute this in terms of elements of the basis, you take the coefficients out, and you get this expression. All right, so now let's talk about the step we take when we move from tensors that are defined at a point in the manifold, right? Taking elements, as arguments, if you want, elements of the tangent and cotangent vector space to the manifold at a point. We can also build the notion of tensor fields, the same way that we built from the notion of vectors that are elements of the tangent vector space at a point, we build the notion of vector fields. Now, a tensor field would be a family of tensors, if you want, at every point of the manifold, such that the components in all coordinate bases are smooth when I move from one point to another. So tensor fields are the ones that I'm going to be calling tensor for most of the course, right? Unless I tell you otherwise. Let's see the little difference here. A 0, 0 tensor, what is that? At a point, a 0, 0 tensor at a point, right, is just a real number, so it's the value of a function, right, from the manifold, is from the manifold to the reals. A 1, 0 tensor would be a tangent vector, a 0, 1 tensor would be a one form. Now, if we extend to tensor fields, we get that 0, 0 tensors are functions. I mean, at every point a different real number. Those are what we call scalars, scalar fields. 1, 0, a 1, 0 tensor will be a vector field, and a 0, 1 tensor will be a one form field, all right, or covector field, depending if you're very physical in the way you give your names. All right, so now, hopefully we understand what a tensor is. How do the components of a tensor change and the change of basis? How do they transform and the change of basis? Well, that's actually pretty easy to find out. So if you want, I can do it. Let's see. So instead of writing the R times and S times, I did this tensor. These are the components of a tensor T. That is 1 time contravariant and twice covariant, okay? So a 1, 2 tensor. And now I want to ask, how do the components of the tensor change and the changes of basis? Well, that's easy. So I know that T prime mu nu sigma is going to be equal to the tensor acting on in the epsilon prime with an index upstairs. So let's call it maybe lambda, I don't know, mu rho epsilon rho. So this thing is epsilon mu prime, okay? And tilde, of course, because it's an element of the dual basis, so it transforms with lambda tilde. Now the element of the basis transform with lambda, and this one we want to have a nu here, and then I wrote a sigma, not a sigma because that's used. I wrote an alpha, and then epsilon alpha, okay? So this thing here is epsilon prime nu, okay? And then here I write lambda, and this has to end, let's get a sigma to end with it, sigma, and then beta, epsilon beta, like that, of course. So this thing is just epsilon prime sigma. All right, so this is a multilinear map. Because it's a multilinear map, I can take out all the elements that are multiplying to the arguments. Wonderful. So this means that this is going to be equal to lambda tilde mu rho, and then lambda nu alpha, and then lambda sigma beta, and then acting on T epsilon rho epsilon alpha epsilon beta. All right, but what is this thing? Well, this thing is nothing but the coordinates of the tensor in the unprime basis is the coordinate rho alpha beta. All right, well, I got the transformation rule. The transformation rule is I write everything. The left hand side was T prime mu nu sigma, it's equal to, and I get lambda tilde mu rho lambda nu alpha lambda sigma beta, and then T rho alpha beta. And there you go. It's exactly as expected from our second video. A tensor that is 1 time contravariant and twice covariant, the components change 1 lambda tilde for the covariant index, and then 2 lambdas for the 2 contravariant indices. All right, very easy. This is something that is simple, but if you haven't done it ever, people get a bit thrown off. Oh, what do you mean you can take them out? Yeah, it's multilinear. That's the definition of a multilinear map. Multilinear means that it's linear in every argument. So, of course, linear combinations and coefficients can be taken out in every argument. All right, I hope that this is understood. Let's see now operations that preserve the nature of a tensor. All right? The first operation we're going to talk about is the symmetrization of a tensor. So the symmetrization of a tensor is an operation that you do on, if you want, on the tensor, in particular highlighting a subset of indices of the tensor, and it's defined as follows: 1 over the number of permutations that you can have between these indices, and then sum over all the permutations of those indices. Now, this is an abstract way of writing it, but very compact. I know that it could be a bit off-putting for people who are not used to that. Let's do a couple of examples to illustrate. So if I have a tensor mu nu, and then I want to symmetrize the 2 indices, what would that be? Number of permutations is just 2, so 1 over 2, and then I have T mu nu plus T mu mu. So yeah, a symmetrization as you probably have heard before. Now, if you were to have three indices, I don't know, mu, alpha, beta, and I want to symmetrize the two first, that would be 1 over 2 t mu alpha beta plus t alpha mu beta. All right, so it's not very difficult. You see, this is it. No more mystery to it. There could be three. Let's see, let's do the three of them. Mu alpha beta, and we can symmetrize the three of them. So in that case, we have six combinations. So 1 over 3 factorial, which is going to be 6. I said combinations, but I mean permutations, of course. And this would be t mu alpha beta plus t mu beta alpha plus t alpha mu beta plus t alpha beta mu plus t beta alpha mu plus t beta mu alpha. There you go. 1, 2, 3, 4, 5, 6. Very nice. So this is the symmetrization. So this is an operation that preserves the tensor nature. So if I have a 3 times covariant tensor on the left, I have a 3 times covariant tensor on the right. So when by that I mean when if I apply symmetrization to a 3 times covariant tensor, I end up with a 3 times covariant tensor. All right, let's see another operation that is similar to this one. All right, the anti-symmetrization. What is the anti-symmetrization? Now we notate it with square brackets rather than round parentheses, right? And it's the same, it's 1 over the number of permutations, sum over permutations, but now you need to add the sign of the permutation. The sign of the permutation, remember, is +1 if it's an even permutation, if I move the indices an even amount of times, and it's -1 if it's an odd permutation, if I move the indices an odd amount of times. Now, with two indices, the example is very easy. I move it 0 times with a plus, I move it 1 time with a minus, so very easy. This anti-symmetrization, okay, same here. With three indices, it's very similar to what we did with the Levi-Civita symbol, if you remember in the first videos that we recorded. Let's see what this is, right? Mu alpha beta, this is a plus sign. This one, mu beta alpha. Oh, I did an exchange of beta and alpha, so this is a minus. Okay, alpha mu, beta is in the same. Oh, this one is a minus as well. Okay, alpha, beta, mu. What did I do here? So I swap mu with alpha and beta with alpha. Action. Wah! So I swap, if you want, twice, right? Mu with alpha and then beta with alpha. So if I do that, then that is a plus. It's an even permutation. All right. Now what about this one? Beta with beta alpha mu. So mu beta alpha. Mu beta alpha is an odd permutation. And this one, B mu alpha, it's mu alpha beta is an even permutation. All right, I can read it. Beta mu alpha, 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 beta. It's the same order. That's the trick with three indices, if you remember to do it. So we got 3 negative signs, odd permutations, and 3 positive signs, even permutations. For more indices, well, you can always do the trick of the graph theory little trick that I told you. So you write mu alpha, beta, that works for any number of indices, right? Let's check the sign of this one. That's the original ordering. Here is alpha, mu, beta. And then you just match them and you count the crossings. There's one crossing, so it's odd, so a minus, okay? And that works for all number of indices. All right, wonderful. Let's see another operation that you have seen at the very least in quantum mechanics. All right, so we define the tensor product of two tensors R of type Rs and T of type TQ. This we define it and we call it R tensor T. And it's a new tensor of type R plus T, S plus Q, so the type sum, right? Now this one, it would be as many times contravariant as R and T combined, and as many times covariance as R and T combined. And we define the components in a given basis as follows. The components of the tensor product are just made up of combining, like this, multiplying, simple multiplication of the components of the individual tensors. Now I have a couple of examples here. So I didn't write this, but I write another one too. This is a couple of examples of tensor products of elements of the basis. You can tell that if epsilon mu is an element of the basis of the vector space, of the tangent vector space, and epsilon super mu is an element of the basis of the cotangent vector space, the tensor product would be a basis for the tensors type 1, 1 in here, and type 2, 0 in here for the tensors. So the tensor product of elements of the basis, indeed, the tensor product of elements of the basis of the tangent vector space and cotangent vector space is what builds the elements of the basis of the space of tensors of higher order. Now, knowing that, I can write the tensor R the same way that I write a vector V as V mu epsilon mu, right, where there's an expansion in a basis. I can do the same with the tensor R. And of course, I need copies of the base of vectors for the contravariant parts indices of the tensor. And I need copies of the basis of Oneforms for the covariant parts of the tensor, right? All right, so I have these two tensors, and I want to compute the tensor product R tensor T. What is that? Well, R tensor T is just, I'll do it like this. It's R mu nu. I'll change the name of these ones because I can't repeat. T sigma rho, and then I will make the basis tensor product between the bases. There will be an epsilon sub mu tensor epsilon nu tensor epsilon sigma tensor epsilon rho, which is what I call it. All right. So this is the tensor product, right? R times T in this example, and these are the components in the basis epsilon mu, and the dual basis epsilon mu. All right, wonderful. So one more operation, that is the contraction of indices between a covariant index and a contravariant index. Given a tensor T, that is R times contravariance, S times covariance of components T, A1 to AR, so R contravariant indices and S covariant indices, we define the contraction of the first pair of covariant and contravariant indices as the tensor R, that is of type now R minus 1 is minus 1, that has these components. I sum over the first covariant and contravariant indices. All right, that's very simple. So I can get, for example, if I have a tensor T mu nu like that, I can define the contraction. This is a 1, 1 tensor, so I'm going to get a 0, 0 tensor. I'm going to get a scalar that is going to be T mu mu, which is the trace, right? If it were a matrix, it would be the trace of that matrix. All right, wonderful. So these are the tensor operations that we're going to see. We're going to end the video here. We're going to continue in the next video. In the next video, we're going to talk about the exterior derivative. We're going to talk about N-forms, not in full detail, but at least a little introduction to them. And we're going to also talk about smooth maps, pullbacks and push forwards, and diffeomorphisms. I'll see you in the next video. Until then, take care.